Today I'm going to show you how to solve some fairly standard problems from Chapter 4 on forces. So the first problem says, a man pushes on a piano, which has a mass of 180 kilograms, so that it slides at constant velocity down a ramp that's inclined at 11 degrees above the horizontal floor. Neglect any friction acting on the piano. Calculate the magnitude of the force applied by the man if he pushes A parallel to the incline or B parallel to the floor. So first of all, let's start off by drawing a picture of what we have. So we have a ramp. The ramp is at an angle of 11.0 degrees above the floor. We have a piano that has a mass of 180 kilograms. It's sliding down the ramp at a constant velocity. Okay, well, there's no friction between the piano and the ramp. And we want to calculate what force the man applies to the piano, first of all, if he pushes parallel to the incline. So let's put on a force of the push parallel to the incline, and then let's solve the problem. Okay, so first of all, let's do part A. So part A, let's draw a free body diagram. So a free body diagram, we represent the piano just as a dot, and we indicate all the different forces that are on it. So our forces that we can possibly have, remember, are weight, tension, normal force, friction. Which of these forces are present? Well, we've got the weight of the piano, mg, downwards, and it's always vertical. We've got the force of the push, parallel to the ramp, and we've got the normal force. Normal force is always perpendicular to the surface of the ramp. What other forces? We don't have any tension because we don't have a string, and we don't have any friction because we're told that we're supposed to neglect any friction. So we only have three forces here. So the next thing that we do is we make up a table. We add up all the forces together to get the net force. Okay, and we always need to choose what axes we're going to use. So in this case, since I have two forces that are either parallel or perpendicular to the ramp, the force of the push and the normal force, I'm going to use my x and y axes tilted so x is parallel to the ramp and y is perpendicular to it. Okay, so let's go ahead and make up our table. Okay, so what I usually do is I make up a chart, show the x components and the y components of each of the forces, and in this case I have three different forces. Alright, let's start with the easy ones. Force of the push is parallel to the ramp, and we don't know what size it is. That's what we've got to calculate. So there's an x component, no y component. The normal force is all perpendicular to the ramp. That's all in the y direction, nothing in the x direction. And now the weight, we're going to have to break up into x and y components. So if we go back and we look at our diagram here, this angle in here is equal to the angle of the ramp above the floor, so that's 11 degrees. So if I draw another picture, let me draw another picture over here. Here I've got mg. Here I've got my 11 degrees. The x component and the y component. This side here is the x component, and you notice it's negative because it's going down the ramp. This side here is the y component, and that's also negative. And so if I look at my x component is this side that's opposite to the angle, so that means it must be sine. Okay, so it's going to be mg sine theta, and we need to put a negative sign. The y component is this side here, adjacent to the angle, it's touching the angle, so it's mg cosine theta, and again that's a negative. Okay, so what numbers do I actually know here? Well, I know m, I know g, I know theta, so I can get numbers for the weight. I don't know how hard I'm pushing with, and I don't know my normal force. Okay, so if I do this, I say, okay, so my sum of my forces in the x direction, just add up down this column. I've got my force push minus mg sine theta. And what does that have to be equal to? That has to be equal to the mass times the acceleration in the x direction. And the acceleration in the x direction in this case is, because if you say that it's at a constant velocity means it's not accelerating. So ax is equal to 0. And also ay is equal to 0 because it's not falling through the ramp, it's not jumping up off the ramp. So I know that my x column has to add up to 0, so that means that the force with which I push has to be equal to mg sine theta. If I similarly did it in the y direction, I get my normal force minus mg cos theta is equal to the mass times the y acceleration, which again is 0. So then my normal force is equal to mg cos theta. And I can go ahead and plug the numbers in. Okay, so I've got 180 times 9.8 times the sine of 11. Put that into my calculator. 180 times 9.8 times the sine of 11. And I get 336.6 newtons. 180 times 9.8 times cosine of 11 for my normal force is equal to 1,731.6 newtons. In part A, I'm only asked for how hard he pushes, so I need just force of the push, and I need to round that off to 3 significant figures, so I've got 337 newtons. Okay, so that's part A, and you notice I didn't even have to find the normal force. We weren't asked for that, but we got it anyway. All right, part B, now I've got my force that's applied parallel to the floor. So now I've got my force of the push horizontal, I've got my weight vertical, and I've got my normal force. The normal force is always perpendicular to the ramp, so that's still going at an angle. So now this time I'm going to make my x-axis horizontal and my y-axis vertical, again so that I only need to find components of one of the vectors. Alright, so let's do this thing. Again, same rules. Force of the push is all in the x direction. No y component. The normal force now is at an angle. We're going to have to find x and y components. And the force of the weight is all horizontal, so it's mg straight downwards. No x component. Okay, so let's draw a picture now and find components for the normal force. Okay, so here's my normal force. This angle in here is 11 degrees. So my x component is this side of the triangle. It's opposite, so that is the sine. And it's also going backwards, so it's negative. So I've got minus Fn sine theta is my x component of the normal force. And vertically, I've got cosine, and it's positive. So I've got plus Fn cosine of theta. All right, what did these columns add up to? Sum of the forces in the x direction is equal to the force of the push minus the normal force times sine of theta. And that's going to be equal to, again, mass times acceleration in the x direction. And since it's moving at a constant velocity, that's 0. So that tells us that the force of the push is equal to the normal force times the sine of 11. And we don't know the normal force yet, so we can't figure out how hard he's pushing. So now we're going to have to use our y equation to find the normal force. So our y equation, normal force cosine of theta minus mg is equal to the mass times the acceleration in the y direction. And it's not accelerating in the y direction, so we get 0. So that means that the normal force times cosine of 11 is equal to mg. And we know mg, m is 180, g is 9.8. So now we can get our normal force. Excuse me, our normal force is going to be equal to mg over cosine of 11. So that's 180 times 9.8 divided by cosine of 11. Okay. Plug that into my calculator. 180 times 9.8 is 1764 divided by cosine of 11. I get 1797 exactly newtons. Okay, so you'll notice that the normal force in these two cases are different. Okay, and that's because he's applying a force that's slightly into the ramp for the second case. So he's sort of pushing the box down into the ramp a little bit, and so the normal force between the ramp and the box is slightly bigger. All right, now I know my normal force. I can put it back in here to give me the force with which he pushes. So now it's normal force, 1797 times the sine of 11. Plug that into my calculator. I get 343 newtons, rounded off to 3 significant figures. So he's got to push a little bit harder when he pushes parallel to the floor than when he pushes straight up the ramp. Okay, the next kind of problem is one where you've got two different objects that are fastened to each other and they're moving together. So this problem, we've got a 15 kilogram load of bricks that's hanging from one end of a rope, and that rope passes over a small frictionless pulley. A 28.0 kilogram counterweight is suspended from the other end of the rope. What's the magnitude of the upward acceleration of the load of bricks, and what's the tension in the rope, and how does it compare to the weight of the bricks and to the weight of the counterweight? All right, first thing I always do is draw a picture. So draw a picture. I've got a pulley. I've got a rope hanging over it. On one side, I've got a load of bricks. There's a bunch of bricks here. It has a mass of 15.0 kilograms. On the other side, I've got a counterweight that has a mass of 28. And let's call these mass 1 and mass 2. Okay, which way is it going to go? Well, just looking at it, you know the heavier weight's going to win. So that means that mass 2 is going to go down and mass 1 is going to go up. What's the acceleration of them? How does it compare? Well, they got to have the same acceleration because they're tied together. So the bricks go up with an acceleration of a and the counterweight goes down with an acceleration of a. So we want to know what's the magnitude of the upward acceleration of the load of bricks and what's the tension in the rope. Okay, so let's break this up into free body diagrams. We've got to do one for each of the two masses and then figure out the forces. So let's first do mass 1. So if I look at mass 1, remember what are our different forces? We've got weight, we've got tension, we've got friction, and we've got normal force. So what's the weight? Well, weight is m1g, and it's always straight down. Do we have a tension? Yes, we've got a rope that's pulling it upwards. Okay. Do we have a normal force? No, because it's not sitting on a surface. Do we have a friction? No, because it's not sitting on a surface. So we only have two forces here, and let me just draw an arrow indicating our net acceleration is upwards. So if I look at this, I've only got a one-dimensional problem. So if I do my forces, so let me write again that this is for mass 1. We have that the tension upwards, I should write that as the force of the tension upwards minus the weight downwards is equal to the mass times the acceleration. Okay, so that's our net force is equal to the mass times the acceleration. And in this case, I don't have to do x and y components because we only have one dimension. All right, let's look at mass 2. Mass 2, I've got a similar looking picture. Okay, there's no normal force, there's no friction because there's no surface. I've got m2g downwards. I've got the tension upwards. And the only thing that's different is that this time the acceleration is downwards. So how do I indicate that? So sum of the forces, I've got tension minus m2g, and again that's a negative because it's downwards. The tension is positive because it's upwards, is equal to the mass times the acceleration, and since the acceleration is downwards, I've got to write that as a negative sign. Okay, so I've got two equations, and I've got two things that I don't know. I don't know my tension, I don't know my acceleration. So if I've got two equations and two unknowns, I can solve the problem. All right, so how am I going to do that? Well, first of all, let me just find my tension in terms of M2 and A. So if I rearrange this equation here, I get force of the tension is equal to minus M2A. And then I'm going to add M2G on the other side, plus M2G. So that's equal to M2 times G minus A, just factoring out the M2. Now I can take that and I can put it into my top equation. So I've got Ft minus M1G is equal to M1A. And I'm going to plug in that the force of tension is M2 times G minus A. And now I want to solve for the acceleration. So I want to get all the terms with acceleration over to one side. So let me first factor this out. So I've got M2G minus M2A, if I put that out, minus M1G is equal to M1A. So now I want to get all the terms with A on the same side. So I'm going to just take this term, I'm going to add it over to that side. So now I've got M2G minus M1G is equal to M1A plus M2A. So on the left-hand side, I've got M2 minus M1 times G. On the right-hand side, I've got M1 plus M2 times A. So now to get my A, I just divide the left-hand side by M1 plus M2. So I get A is equal to M2 minus M1G divided by M1 plus M2. And we can get a number for this because we know the two masses and we know G. So my acceleration is M2, that's 28 kilograms, minus M1, 15.0, divided by 28 plus 15.0 times G, which is 9.8 meters per second squared. And so I get 28 minus 15, so it's 13, divided by 28 plus 15, that's divided by 43, times 9.8. I get 2.96 meters per second squared as the acceleration. And I leave that with three significant figures because our two numbers up here for the masses have three significant figures. All right, second part says what's the tension in the rope? Well, the tension in the rope we said was M2 times G minus A, and now we know A. So force of tension is M2 times G minus A. So M2 is 28, G is 9.8, A is 2.96. So 9.8 minus 2.96 is 6.84 times 28. I get 191.52 newtons. And I got to round that to 3 sig figs, so I'm going to round that up to 192 newtons. Okay, so now I've got my answer to the two problems. Now it asks, how does this tension force compare to the weight of the brick and the weight of the counterweight? Well, the weight of the brick is the mass of the bricks times 9.8. So that's 15 times 9.8. And that's 147 newtons. Okay, so the tension force is bigger than the weight of the bricks. How about the weight of the countermass? Well, that's going to be M2 times G, so that's 28 times 9.8, which is 274.4 newtons. So the tension in the string is smaller than the weight of the counterweight, but bigger than the weight of the bricks. Okay, the third type of problem in this chapter is one in which we have friction. So let's do a problem here. We exert a 100 Newton force on a 25 kilogram box to move it along a horizontal floor. The coefficient of kinetic friction between the block and the floor is 0.25. What's the acceleration of the box if the 100 Newton force is exerted horizontally, if it's exerted at an angle of 30 degrees above the horizontal, and if it's exerted at an angle of 30 degrees below the horizontal? So we're going to have to break this up and solve it 3 times. So first of all, let's start with part A, and let's draw a picture. It's meant to be a horizontal line. I've got a box on it, has a mass of 25 kilograms, and I'm exerting an applied force of 100 newtons parallel to the floor. So let's do our free body diagram. So draw the box as a mass, and then figure out what forces we have. Well, obviously we've got our applied force. What else do we have? Well, we have a weight that's downwards, and that's equal to the mass times g. It's sitting on a surface, so we're going to have a normal force that's perpendicular to the floor, which in this case is horizontal. And then we have a frictional force. Frictional force is parallel to the surface, and it's opposite to the direction of motion, so it's in that direction. Alright, so we've got 4 forces. Make up our table. Okay, so we've got x and y components. And in this case, the obvious choice is x horizontal, y vertical. So applied force of 100 newtons is all going to be in the x direction, no y direction. The frictional force is going to be minus mu k times the normal force in the x direction, 0 in the y direction. Normal force has no x component, all y component. We don't know how big it is, so I can't put in a number yet. And the weight is all in the y direction, and it's downward, so it's minus m times g. And I know m and g, so I could put in a number here, but right for now, let's just keep it as letters since it's a bit easier to write. So next thing we do is add up down the column. So add up down the x column. Sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. And we know that that's going to be over towards the right there. We don't know how big it is. And that's equal to 100 newtons minus mu k times the normal force. And we don't know the normal force, so we can't put in what our numbers are. We can't figure out the acceleration. We do know the mass. Alright, sum of the forces in the y direction. And you'll notice here I wrote down n instead of fn. Remember, I should always try to write the normal force as fn, so I'll try and do that from now on. Alright, add up down the y column. I've got normal force minus mg is equal to the mass times the acceleration in the y direction. What's the acceleration in the y direction? It's 0. The box doesn't leap up off the floor. It doesn't fall down through the floor. There's no vertical acceleration. So no vertical acceleration, and that means that the normal force is just equal to m times g. And now let's plug in our numbers. So 25 kilograms times 9.8 meters per second squared, and I get 245 newtons is my normal force. Now I can take my normal force, I can plug that up in here, and I can get my acceleration. So if I look at this equation here, I've got mass times the acceleration in x direction is equal to 100 minus mu k, which is 0.25 times the normal force. Okay, so I'll plug that into my calculator. And I get 38.75 newtons is equal to mass times the acceleration in the x direction. So the acceleration in the x direction is 38.7 newtons divided by the mass of the object, which is 25 kilograms. And I get 1.55 meters per second squared. And I've got 3 significant figures here, 4 significant figures there, 2 there, so I need to round that to 2, so it's 1.6 meters per second squared if I push horizontally. Okay, so that's my answer for part A. Part B, what happens if I pull it up with a rope or something at an angle of 30 degrees? So now here's my picture. I'm going to draw my applied force. It's going to be this direction at an angle of 30 degrees. So now my free body diagram, my normal force and weight and frictional force, those don't change their direction. The only thing that changes its direction is the applied force. So what changes in my table? Well, the only thing that changes in my table is that my applied force, now in addition to the x component, is going to have a y component. So I've got the force is at 30 degrees. So my applied force of 100 newtons is going to have part of its component vertically and part horizontally. The horizontal component is this side here. It's adjacent to the angle, so it's going to be 100. That's my applied force times cosine of 30. And the y component is going to be opposite, so it's 100 times sine of 30. So we can get a number there. Frictional force, again, it's going to be minus mu k times the normal force in the x direction, nothing in the y direction. The normal force is all going to be vertical. We don't know how big it is. And the weight is going to be minus mg. So now we have our table made up. We do the same thing. Sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. And we want to find the acceleration in the x direction, so we don't know that yet. So go down that column. I've got 100 cosine 30 minus mu k times the normal force. I don't know my normal force, so I can't figure out what the acceleration is. Sum of the forces in the y direction is equal to the mass times the acceleration in the y direction, and again, it doesn't jump up off the floor, it doesn't fall through the floor, no acceleration in the y direction. So this total column here has to add up to 0. So I've got 100 sine of 30, which is just a number. I've got my normal force, which I don't know, minus m times g, and I do know that. Okay, so my normal force, rearranging that equation, is mg minus 100 sine of 30. mg is 25 times 9.8 minus 100 sine of 30. So my normal force now is equal to 245 minus 50, or 195 newtons. Now I can take my normal force, put it back up into this equation. So I put it back up into that equation. So I get my mass times my acceleration x direction is equal to 100 cosine 30 minus mu k times the normal force. So I've got 100 cos 30 minus 0.25 times 195. And I get 37.85 newtons is equal to the mass times the acceleration. So my acceleration is equal to 37.85 divided by the mass, 25. And so I get 1.51 meters per second squared. So in case B, it's accelerating slower than in case A. Why? Well, because in case A, we're applying the force directly in the direction that we want to move. In case B, we're applying the force at an angle to the direction that we want to move, so not all of it is applied in the direction we want to move, and so the net acceleration is smaller. Okay, so let's do the last case. We're going to need another piece of paper. So in the last case, what's changed is that now we apply our force downwards. And so you can imagine that this is something like you're pushing from the back and you're slightly leaning down onto the box. So now, if I look at my free body diagram, I've got normal force up, I've got the weight downwards of mg, I've got frictional force backwards, all those are the same. The only difference is that now my applied force is downwards at an angle of 30 degrees. So make up our table, just like we did before. Put in our 4 things. Alright, so applied force is 100 newtons. And now it's going to have a y component that's negative because it's downwards, and an x component that's across. So I've got 100, and again this side, the x side, is adjacent to the angle, so it's cos 30. The y component is 100 sine of 30, and it's negative because it's downwards. I've got my frictional force is minus mu times the normal force. Again, no y component. Normal force, 0x component, all y. And the weight, 0x component and minus mg in the y direction. Alright, so our table looks slightly different, but we do the same thing. Add it up. Sum of the forces in the x column have to equal to the mass times the acceleration in the x direction. Again, we're trying to find the acceleration in the x direction. So add up that column. We've got 100 cosine 30 minus mu k times the normal force. So that looks exactly like the previous example. And again, we don't know the normal force, so we can't get our acceleration. Get the normal force, we've got to look at the y column. Sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. And again, there's no acceleration in the y direction. The box doesn't fall through the floor, it doesn't leap up off the floor. So add up that column. Now I've got minus 100 sine 30 plus the normal force minus mg. So I've got my normal force is equal to mg plus 100 sine of 30. So now that's 295 newtons. Put that normal force back up into here. So again, we're just following the same steps over and over again. So acceleration in the x direction is 100 cos 30 minus mu k, which is 0.25, times the normal force, divided by the mass. So on the top, I've got 100 times cos of 30, which is 86.6 minus 0.25 times 295. I get 12.85 over 25, which is 0.514 meters per second squared, and I've got to round that to 0.51, keep 2 sig figs, meters per second squared. So if I look at the three cases, A, B, and C, let me bring them back. Okay, so in case A, my normal force was 245 and my acceleration was 1.6. Here the normal force was just equal to the weight. In case B, I was pulling slightly upwards, and what that was doing was slightly lifting the box up off the floor, and now my normal force was 195. It was less than the weight, and my acceleration was smaller because I was pulling the box at an angle. And again, here I should have rounded my acceleration to 2 sig figs. I should have left that as 1.5 meters per second squared. All right, in part C, now my normal force is bigger than the weight. It's now 295 newtons. Why is it bigger than the weight? Well, because I'm sort of leaning down on the box as I push, and so now the floor has to push back up on the box with a force that's equal to the weight of the box plus the downwards force that I'm applying when I'm pushing down on the box. So now my normal force is bigger, and that's going to make my frictional force bigger. So my frictional force is bigger in part C, smaller in part B. And my acceleration is smaller in C than it is in either A or B for two reasons. One is because I'm applying my force not straight across, it's going partly downward, so it only has a component pulling it forwards. And the second thing is because I'm pushing slightly downwards on the box, I've also increased the frictional force backwards, and that's slowed it down some more. So hopefully with these three problems, plus working lots of problems from the book, you should have a good grasp on doing force problems for the test.